Good morning everybody. Now, we will have the continuation of our earlier discussion. We were discussing the nucleation process due to the presence of heterogeneous cavities for which act as the nucleation site. Now, we will proceed with that discussion only. Now, if you recall that sometimes back I have given you the boiling curve, the very famous full boiling curve, and if it is a heat flux controlled process, then the boiling curve will be something like this. So, the transition region we will not be able to we will not be able to catch the transition region, but let us say we have got different notations. So, A to B is the natural convection or free convection, cooling due to natural convection or free convection, and B to C is the nucleate boiling curve on this particular plane, where we have got the variation of heat flux as a function of delta T, which is nothing but T wall minus T saturated. So, on the nucleate boiling curve B C, we get different regimes of boiling, this also I have told. Now, the first regime which I get probably up to this point, that is the regime of, let us say we call it some D. So, B D is the regime of boiling due to isolated bubbles. So, here if I idealize the process, let us say this is the hot surface, here we have got different kind of nucleation sites, something like this, and on each of these sites, these are actually, there could be many more sites, but these are activated sites based on the operating condition. So, on each of the sites we are having some sort of a bubble. Okay. So, this is your state of isolated bubbles or boiling due to isolated bubbles, and you can understand that this is due to heterogeneous nucleation. On the heater surface there are different cavities which have been activated, and we are having this. Now, basically in this isolated bubble region, one bubble is not influencing the growth or the heat transfer process of another bubble. That is one of the assumptions. So, that means you can do the analysis based on what is happening to a single bubble. So, that kind of analysis already we have done, and we will proceed some more or we will discuss some more regarding the same process. That means that there is an isolated bubble which is growing, and then there is heat transfer process and phase transfer process. Now, you see the one particular nucleation site, if we observe or if we concentrate on a particular nucleation site, then what we will see that the process is a cyclic process. It is a repetitive or cyclic process. So far we are keeping the condition constant. So far we are keeping the condition constant means we are keeping the wall temperature constant. It is a dynamic process definitely, but we have kept a steady operating condition, that means the wall temperature we have kept constant, the heat flux imposed to the wall that we have kept constant. If we do that, then we will find that more or less a repetitive process is taking place at the mouth of a particular nucleation site. Okay. So, the process is a cyclic process. So, what is the cyclic process? What are the component of the cyclic process? First is nucleation, then second one is bubble growth, and third one is bubble departure. So, these three processes will take place over and over. So, once it will nucleate and then we will see a growth, it is also following a pattern which we will discuss, and then it will depart. Okay. And the time involved is, that time can be divided into two parts. If the time we denote as T cycle, then it is T waiting plus T growth. There is a waiting time which we can think of, or which we can call as the preparation time for the nucleation of a bubble or for the formation of a bubble. And then there is time for growth, and of course, departure is instantaneous phenomena. Departure is a very important phenomena, but it is instantaneous phenomena. So, there is no time for departure. As it grows to a particular size, then it will depart. Okay. So, this is the process which will take place. So, TWT is the waiting time and TGR is the growth time, and T cycle is the total cycle time. So, then you see, we can also calculate the frequency of bubble formation. So, frequency of bubble formation, if we call it FB, so that will be 1 by TWT plus TGR. So, the frequency of bubble formation also we can calculate. So, once we have calculated this, or once we know this, then what we can do? We can have a rough estimate of the heat transfer during nucleate boiling, particularly in the isolated bubble region. So, you see, the boiling curve what I have drawn, this is a relationship, or this shows the function, this shows the variation of heat flux with Tw minus Tsat. So, this generally is determined from experiment, but suppose we want to do it theoretically, at least for this part of the curve, we will see for the other parts of the curve later on, but at least for this part of the curve we can determine theoretically what is the value of Q double prime, what is the value of wall heat flux. How can we do it? A very simple equation can be written. For isolated bubble, we can write Q nucleate boiling, that is equal to capital N F B rho g H L V, rho g or rho v, whatever you may like it, pi by 6 and d B d whole cube. So, what are the different components here? N is the nucleation site density on the surface. N is the nucleation site density on the surface. Fb is the frequency, already I have told that frequency of bubble formation or bubble departure. Rho g or rho v, I mean you can represent it by rho v also. So, this is the density of the vapor phase. HLV is the latent heat of vaporization, and the last part that shows the volume of a particular bubble. Okay. So, you can see that dimensionally it will also give you the heat flux value which is there on the left hand side. Now, how are we going to determine all these things? Rho g and HLV, they are properties of the fluid. FB, that is the frequency of vapor bubble formation or vapor bubble departure. Now, this frequency again it depends on two times, one is the wetting time and one is the growth time. So, already we have got some growth model, already we have discussed that the growth, bubble growth could be either inertia controlled or it could be heat transfer controlled or thermally controlled. So, some sort of equations we have already seen, some sort of analysis we have seen. So, one estimate of FB can be made from there. Now, dBd is the bubble volume at the, it is based on the diameter at the departure. Again I will explain how it can be estimated, but from some sort of force balance one can estimate the volume of the bubble at the departure. Then remaining is N. N is the density of the activated nucleation sites on the particular surface on which boiling is taking place. Now, N is the most crucial of all these components. How to estimate N? Because N is a surface characteristics which comes from many things, which comes from the process by which the surface has been manufactured, the contamination through which the surface has gone, that means the amount of oxidation etc., amount of fouling that has taken place on the surface, and of course, the number of activation site also will also depend on temperature, as I have described in our last class. So, you see that this is one of the very crucial point which we do not have a very straightforward method for determining, though there are models. So, those are basically statistical model. So, roughly one can calculate or estimate what is the number of nucleation site on a particular surface. So, you see then this equation gives us a method, a mechanistic method for estimating the heat transfer during nucleate boiling. That is why we have learned all these things, this bubbling process, what are the different growth model. So, ultimately as an engineer we have to find out the heat transfer coefficient, but the process is complex. There are many more intriguing phenomena which are taking place both from the heat transfer point of view and from the fluid flow point of view. So, what we have done, we have segmented it into small parts, so that each of the part can be analyzed little bit conveniently, little bit easily, and then ultimately if we integrate them, if we collate them, then we can find out the heat transfer coefficient, which is an engineering requirement. Well, I will come to other models, not today, maybe in our next class, but at least whatever we have learned, the bubble growth and different growth process etc., that gives us some means of calculating the heat transfer coefficient. Now, let us try to see whatever I have explained, that there will be a cycle of bubble nucleation, bubble growth and departure. So, let us see that cycle in a little bit detail. So, let us say we start with this particular process. This is a solid surface and we have got, as I have told, thermal boundary layer. So, this is the heated liquid, this is the heated liquid, and what happened, already a bubble have departed this surface. So, when it has departed, it has taken this much amount of heated liquid along with it. So, it has taken this much amount of heated liquid along with it. So, we can tell that this is our first phase. Let us say this is A. Here the temperature is T infinity, here the temperature is T wall, and this temperature is higher than T infinity. This temperature is higher than T infinity, and then actually at time T is equal to 0, this phenomena is occurring. What is time T is equal to 0? One bubble has just left and the next cycle is starting, that is called T is equal to 0. So, at this moment two incidents are very important. One incident is that the bubble which has left, it has the bubble which has departed, it has left a small portion which will act as nucleation for the next bubble. And second thing, it has taken away the liquid of the thermal boundary layer. So, that is why your waiting period is needed, because here the liquid is to be heated back to the temperature which was earlier there, which is a higher temperature. So, that is why a waiting period is required. So, at the end of the waiting period, which is the next phase, what we will find is this. Probably there is a very small protrusion of the bubble, and then we will have this thermal boundary layer which has been punctured. By this time it has been repaired, very small protrusion of the bubble, and thermal boundary layer has been repaired. And if you take the temperature profile, the temperature profile is something like this. Here it is T infinity, here it is T wall. So, this is very important. At this point we are coming back again and again that the superheat is very important, and if you see this particular bubble. So, let us say the way I have drawn slightly, let us modify this diagram slightly. Let us say this has created some sort of a jagged liquid layer over the bubble, not exactly rectangular whatever I have drawn, but maybe some sort of some shape like this. So, suppose here I want to know how the temperature variation is along this radial line. So, it will be something like this. This is your T sat, this is your T infinity. At least physically you have to understand the process. So, at the interface the temperature is the saturation temperature, and the saturation temperature is lower compared to the surrounding fluid temperature here, and of course, it is a boundary layer kind of a situation. So, this temperature gradually decreases and it becomes T infinity, which is the bulk fluid temperature. Now, why it is necessary? See, T sat has to be lower than the local fluid temperature over here, otherwise there will not be any heat transfer and there will not be any bubble growth. So, the bubble growth is taking place because the interface temperature is smaller or is lower compared to the fluid temperature which is just outside the vapor liquid interface. And then again you move along the thermal boundary layer, the temperature will reduce and ultimately it will go to the bulk fluid temperature, which is T infinity. So, these are the first two phases. Here I can write T is equal to TWT. So, this is at the end of the waiting period. So, this is at the beginning of the waiting period, this is at the end of the waiting period. So, after the waiting period, the growth period comes. So, the growth period if I see, it has got two phases. So, here of course, T is greater than T waiting, but this is phase 1. So, in the phase 1, the growth is inertia controlled, and here what we will find, here we will find that the vapor bubble will grow almost hemispherically. It will grow almost hemispherically. So, this as we were pointing out, so this may be termed as C. So, A was at the beginning of the waiting period, B was just the waiting period is over, and C that the initial growth, that is phase 1, it is beyond the waiting period. In this period, the bubble growth, the bubble shape is hemispherical shape. Now, let us try to understand, now we know the temperature etcetera. Let us try to understand what is inertia controlled growth, though we have done the mathematics etcetera, but once again let us try to see. See, initially when the bubble forms inside the thermal boundary layer. So, this is the thermal boundary layer. T wall, that is the highest temperature anywhere we are considering, the phenomena, T wall is the highest temperature, and we are having the bulk temperature which is lower. Here we are having T sat. So, T sat is the saturation temperature corresponding to the existing pressure. Now, as the T wall is very high, here also temperature is very high. So, what we can find, that there is a large temperature gradient. T sat is really low compared to the surrounding fluid temperature. So, due to this high gradient, what will happen? There will be large amount of heat transfer. The vapor growth will be, or the bubble growth will be fast, and this we have learnt earlier, that inertia controlled regime, the bubble growth is faster. Why it is inertia controlled? Because as the heat transfer is very fast, heat transfer is not putting any sort of limitation to its growth. To the bubble growth, heat transfer is not putting any limitation. Limitation is only put how fast the gas can expand and the interface can move apart, so that the bubble can become bigger. So, that is why it is called inertia control. Heat transfer is really helping it. So, at this time heat transfer is not opposing it, and we will have a faster growth. But the bubble shape will be kind of mushroom shape or hemispherical shape, the way I have shown. All right. Let me draw it in a bit detailed manner. If I take, so basically if I draw it in an exaggerated manner, so you will get some sort of liquid over here, and this is your vapor. Okay. So, basically then you are having, you can imagine that you are getting some sort of wedge kind of a shape, and this is called evaporation microlayer. So, there are many models that they model this micro layer, and now the bubble growth is mainly due to evaporation from this micro layer. This is a micro layer. So, there will be evaporation from this micro layer, and you can understand that it is very, very thin. Actually, where it comes close to this nucleation site, it is in the molecular level. So, many people have modeled it, mechanistic modeling is there. Even nowadays people are doing CFD modeling. So, people argue that a single scale for modeling is not sufficient. Probably very near this vapor stem, this is the vapor stem, one has to go for some sort of molecular scale modeling, then some sort of intermediate scale modeling, and then one should go for some macro scale modeling, then only this process can be modeled, because here it is very thin in the molecular level. Now, what you can understand that if it is very thin, of course, even in the macroscopic level also it is very thin, then the heat transfer will be by conduction. By conduction analysis one can catch what is the amount of heat transfer. Now, if there is only conduction, conduction is the predominant method of heat transfer, then there is no, we are assuming that there is no fluid flow. So, fluid is also not replenishing whatever evaporation. So, from this surface evaporation is taking place. Okay. Now, it is not being replenished because we do not have much flow, much liquid flow we do not have, this is a very thin region. So, what will happen? Depending on the operating condition, the initially my micro layer have started from here, then some sort of dry out will take place, then some sort of dry out will take place. So, that means after some time your dried zone could be like this. Okay. Now, it will depend on the operating condition, and let us say that very close to this there is another bubble. So, then these two bubble can coalesce and intermediate range, intermediate area can be totally dried up. That means, here there is one bubble and very close to this there is another bubble. So, they will intermingle together to form a bigger bubble, and entire place will be dried below these two vapor mushroom. So, depending on the operating condition, depending on the situation of heat flux, wall temperature, etc. So, you see how we are going from the isolated bubble region to the slug region or to the columnar bubble region. So, now it will make not a vapor bubble, but a column. Okay. And ultimately, if this process continues, then it will go to critical heat flux type of condition. Okay. That we will discuss later on. So, but what we have understood that at the first stage of growth we will have inertia controlled growth. Why inertia controlled growth? Because the rate of heat transfer is quite high at the first stage. Then if we go to the second stage of growth, we will have something like this. So, here already what has happened that this is also T greater than T waiting period, but second phase. Already what has happened, the temperature in this vicinity of this bubble, that is not very high, that is higher than the saturation temperature, but that is not very high. So, as that is not very high, then the heat transfer now it has become slower. Evaporation has also become slower. So, now this bubble growth is not inertia controlled, it is heat transfer controlled. Okay. And another thing also you can see, the bubble has, I have represented the bubble as a spherical bubble. Why I have represented the bubble as spherical bubble? Because now from the lower side heat transfer has really reduced. Now more or less uniformly heat transfer is there all over the periphery. So, the bubble has become some sort of a spherical bubble. But one thing you have to remember, these are all ideal discussion based on some ideal model. In actual practice you will get something in between. Okay. So, this has become the spherical bubble. Now, the forces which are acting on the bubble one is your capillary force, and two, all the other forces I am clubbing together. There could be lift, there could be drag, there could be inertia. So, generally what happens, that capillary force tries to attach or keep the bubble fixed to the surface. Capillary force acts over here and it tries to fix the bubble along with the surface, and the other forces generally tries to push the bubble away from the surface. Generally capillary force is larger, or rather relatively larger when the bubble is small, and when the bubble is large the other forces that start dominating. So, as the bubble grows, so what will happen, the other forces will dominate and at one time the bubble will depart. So, the bubble departure is the next phase. We can have a schematic view of that. See, this bubble is departing. So, probably it will have some sort of a liquid surrounding this. Okay. So, this is your d T at T d at departure. So, bubble will departure. So, this will complete a cycle and this cycle will continue. Okay. Now, as I have described, I have told that these are based on some idealization. So, as I have described, ideally I have told that it is inertia controlled and then it will be controlled by the heat transfer process, but actually it need not be so. I mean, depending on the working condition, either it can be inertia controlled or it can be controlled by the heat transfer process, or in other words inertia controlled process could be very small. The mainly the bubble growth is dependent on the heat transfer control process. Now, if we see, if we list down the parameters which are responsible for bubble growth and when we can have inertia controlled growth, these are like this. Inertia controlled growth. First, it needs high degree of superheat at the wall. That means high wall temperature. Second, it needs high imposed heat flux. High imposed influx. Third, it needs highly polished surface. That means limited number of active cavities, limited number of active cavities. Then then very low contact angle. So, what does it mean? Very low contact angle means it is having wetting fluid. Fluid is highly wetting fluid. Then low latent heat, and then low density. So, if these factors are there, then we will have inertia controlled growth. Means suppose we want to use a particular model for some sort of design calculation or not, or some such thing, then should we go for inertia controlled growth or should we go for temperature heat transfer controlled growth? So, if we decide that we will adopt only one model, then probably these things we have to check. Okay. Now, you see, it is very easy to explain why it will be inertia controlled when this kind of operating conditions are there. High degree of superheat. So, high degree of superheat means the wall temperature is very high, the surrounding liquid temperature will be very high. So, heat transfer will be predominant. High imposed heat flux is also the same thing. Highly polished surface, what it will give? That means it is giving limited number of active cavities. So, very near, I mean close to one cavity, there is no other cavity. So, one cavity means one vapor bubble. So, only one vapor bubble is there, and then far apart there are other vapor bubbles. So, the particular vapor bubble is surrounded by a very large mass of heated liquid. So, the growth will not be controlled by the heat transfer. Okay. It will have enough supply of thermal energy. Very low contact angle is also the same implication, is also having the same implication, and the last two, the low latent heat and low density, that means the vapor generation is much easier. So, vapor growth will be much faster. Now, first 4 points give a high degree of superheat during the wetting period, and the last 2 points give a faster growth of vapor bubble. So, when there is a combination of these two, then we will have inertia controlled growth. The reverse is true for your heat transfer control growth. So, we can quickly write the condition. We can quickly write the condition. It will be low degree of superheat or low wall superheat, low imposed heat flux, more number of nucleation sites, non-wetting fluid, then you will have high value of latent heat. This will slow down the process of growth, and then high value of vapor density. Okay. So, these are the factors by which we will decide that whether we will go for heat transfer control growth or not. Okay. Now, let us see some more equations which can be utilized for the analysis of this process. Now, let us come to the heat transfer controlled growth. So, as I have told, heat transfer controlled growth or the heat transfer process, we are we are analyzing considering one dimensional transient heat conduction. So, 1D transient heat conduction, we are having dt dt is equal to, this is thermal diffusivity of the liquid d2t dt2. Now, the analysis what has been done, I mean already we have written the equation and shown you the boundary conditions earlier, but slightly in a different way the boundary conditions have been written here. What has been assumed? Which one? Please, del T2 by, oh, del, yes, y or y direction we have taken along the direction of this one, thermal boundary layer away from the wall. Thank you. Now, as I have told that we have done it earlier, but slightly different boundary conditions we are going to take. See, what it is assumed that the time count starts from the growth of the bubble. Time count starts from the growth of the bubble. So, what we can write that T y this is actually time, this is equal to T infinity. Okay. And T at infinity, that means beyond your thermal boundary layer at any time, this is also T infinity, and T at the wall at any time, that is T wall. So, same boundary condition we are putting, only here it is important because from where we are, from which instant we are counting time. The solution can be obtained, this is classical solution, solution by conjugate error function. So, this solution we can get by conjugate error function. First, instead of writing the conjugate error function, let us show that during the two phases what will be the temperature profile. This direction is the y direction and this is your temperature as a function of this. So, the solution will be something like this. This is your T infinity, if we like to put it, and this side your time increases. So, this is for the first phase, already this type of diagram I have shown earlier. Okay. In the second phase or what we can tell that this also holds good for the waiting period when we are repairing the thermal boundary layer. In the second phase or in the growth phase, particularly when it is heat transfer controlled. So, what we will get? We have started from this curve, this is your temperature, with time we will get something like this. This is your T infinity basically. And this is actually all the curves are starting from some sort of a value here, which is T sat. What I am drawing here is the boundary layer T sat, then it is increasing and then it is going to the T infinity. So, this is your T sat. Now, as it is transient conduction, so this is not a stationary picture, this picture will change, and that is what has been shown in the diagram below. So, mathematically what you will get is this: T y t is equal to T infinity, anywhere temperature will be more than T infinity within the thermal boundary layer, T w minus T infinity conjugate error function ER F c alpha L T plus T waiting. Minus T infinity minus T w minus T infinity conjugate error function So, by this particular expression we will get the variation of temperature with respect to time and the direction y. All right. Now, actually what can be done with these equations, one can do little bit more simplification, and then what one can do, one can also predict how the radius of the bubble that is growing. From the vaporization rate, what can be predicted from the temperature equation? This is the temperature equation what we have got. So, if this temperature equation we know, then what we can predict? We can predict what is the temperature gradient, K into temperature gradient, that will give you the heat flux at the bubble interface, and if that heat flux is related to the phase transfer, then we can get at what rate the bubble radius is increasing. So, doing all these things, one can get the expression for the bubble radius as a function of time. That is what I am going to write. That will be a function of Jacob number, which I have already defined. So, all sorts of temperatures are important here, that means wall temperature, saturation temperature and the bulk liquid temperature, and with this the times are also important. This is the waiting time by the time at which we are interested to know the bubble radius. Okay. So, by this then we will get what is the radius of the bubble, how does the radius of the bubble changes with time. Okay. Now, here one can make one assumption. Suppose I want to estimate the waiting period. So, estimation of waiting period. So, basically this is TWT, I want to estimate the waiting period. How I am going to estimate the waiting period? Now, the temperature that will exceed the equilibrium superheat for the bubble, then our growth will begin. Bubble growth will begin when the temperature exceeds the equilibrium superheat temperature. And from where the growth will begin? Growth will begin from a vapor nucleus which is there on a cavity of radius RC. So, you see two things are important here. For a particular cavity, that cavity radius RC is important, and also the equilibrium superheat temperature, that is important. Now, earlier whatever relationship we have got, taking a particular RC value, if we want to manipulate this equation, then we can find out the waiting time. So, waiting time we can write like this: TWT, that is equal to 1 by 4 alpha L RC. Waiting time will be different for different cavity radius. This is temperature T sat minus T infinity by T wall minus T infinity plus 2 sigma T sat V V minus, I think I have to write this part separately, otherwise it will not be clear. So, let me write it under the, so basically this part will be RC divided by ERFC conjugate error function T saturated minus T infinity T wall minus T infinity plus 2 sigma T saturated V V minus V L by H L V and R C. So, basically this will be within bracket and this is, there is a square. So, this is how we will get the waiting time. Okay. Now, it is a very tedious way of matching these two equations and then to find out the waiting period, but one can get the waiting period by this particular equation. There could be a simplified equation for waiting period also. Let me write this. I think you will be more comfortable with the simplified equation, that is 9 by 4 pi alpha L T W minus T infinity R C rho V HVL. So, some simplification of the above equation, earlier equation will give you this simplified relationship for waiting period. So, waiting period also we could get some sort of a equation. Then another equation I like to give quickly, so that we can complete today's discussion. The bubble departure, at bubble departure, what is the diameter of the bubble departure? So, if I denote it by d subscript b d, then there are again number of formula, but one formula, very simple formula if I give, here theta is in degree. This is some sort of empirical formula, not totally mechanistic derivation. So, here it is theta is in degree. So, that means in by today's discussion what we have got some analysis which can give us the waiting time, by which we can also calculate the growth time, departure diameter. So, ultimately the first discussion which we have started, that we can estimate the heat transfer during nucleate boiling. So, using this correlation we can try to do that, at least approximately we can try to do that, in isolated bubble region we can calculate what is the heat transfer coefficient or what is the heat flux